Oh, can you all see now? Can you all see it now? This random scribble.
Yes, yes.
Okay.
Like some random red
Okay.
lines.
Cool. Okay. So, as I was saying, imagine you have two nodes U and for like two nodes U and V, what you want to do is that you want to find out the bigger group of like, for example, the bigger group of like okay, let's say this is U1, this is U2, blah blah. The bigger group which the its UFDS belongs to, because everything when you traverse through here, everything your score just increases by 0, so like it doesn't really matter. Then V, you also find the biggest group where you are. So let's yeah. So this is P. So this is what we call P of V, and this is what we call P of U. Now we can guarantee. Now if P, so what happens is that your DP, if it is defined for U, then like you check if it's defined for U, and then if it is, you can now find DP of V, because you can ask yourself, can I connect this to this? Will it be optimal? So for each V, what you do is that will it be optimal to connect this to this? Yeah. So because you wouldn't connect this to this because this will reset your score to 0. This will increase your score. So what happens is now Mac it's do, this your option this is your option to not connect, basically just store its own value. Or what happens is that you have DP of U plus 1, because now your score increases by 1 for a unique AU. So this is literally everything you need to do for with regard to DP. So it's DP of, basically this should be set to parent of V actually. Then this should be set to parent of V, parent of U. Then your answer is just DP of P of n minus 1, so that you can go from 0 to n minus 1. Yeah, that's literally it. So like yeah. Okay, let's head to skiing. Because yes, okay, skiing. Oh, we forgot to put the statement, bro. Okay. So I hope you have read the statement. Uh, so essentially, what you have is that. Wait, do I go through this?
Or if you want.
Do you want to go through this?
Okay. Alright, so basically this problem uses Dijkstra, but it's more complicated because you can't directly use Dijkstra, because the happiness can actually like either go up or go down. So that means it has, if you want to think it of like as edges, you'll say like this graph has negative edges, which means you can't use Dijkstra because it's not, it doesn't go well with negative edges. So we need to do something to make sure that we don't have any negative edges. So basically, instead of just taking the happiness, we can take the happiness plus the altitude. So like from the question, we know that if the altitude decreases, the happiness increases with like an equal magnitude. So like in the end, this total value, happiness plus altitude, is still the same. So like there's no change. But this is good because it's not negative. And if the altitude increases, his happiness will like decrease a lot more. But so his happiness, because it decreases a lot more, like twice that of his, twice the difference in altitude. So that means that if we just take this total like this, it's still gonna be negative. So what we can do is we can multiply everything by -1. So now it's like you can think of it as like the happiness plus attitude that he loses. So we want to, if the attitude decreases, he loses this happiness plus attitude value. He doesn't lose anything. But if the altitude increases, his happiness will decrease much more. So he will lose a positive value. So in the end, you're basically trying to make sure that the this like decrease is as small as possible, and we can do that with our single source shortest path, aka our Dijkstra.
Yay.
Yay.
Yeah, it's a bit of a difficult contest, to be fair. Yeah, I think I guess we can like pause here for a bit. Then after that, we'll start at like 2:30. Do I stream the remainder of the lesson? I guess I do.
If you want to do that, it's fine.
It's yeah, I'll just do that. It's fine. Okay, I does it turn black now?
I think you have to wait for, yeah, it turned black now.
Okay, sure, cool.
We finished 2D static sum already, and then we are now on we are today we are moving on to max sum.
Did we teach like 3DP yesterday?
No, because 3DP is like after, because like it's DP, because it has DP, so you have to like teach DP first before we teach 3. Alright. Okay, so like first of all I want to say that I checked the Collect Mushroom 6 just now, and like not a lot of people attended it. So yeah, if we yeah, but we don't really have time for that anymore. So we're gonna move on to 2D max sum. So basically we basically want to find the maximum rectangle. So how do we do this? First we basically pre-compute all our vertical static sums. So basically like all the possible vertical static sums. And then so that like just like our normal static sums, we can find a certain block of this by taking like a minus b. Now to calculate our max sums, we basically we take x1, x2. So for everything, so from x1 to x2, we calculate the columns. So that means, so basically we just do, essentially is 2D max sum is just 1D max sum, but like d- like done like in 2 dimensions. Yeah, that's crazy. I know. Alright, so basically we just calculate for every possible x1 and x2, we just do 1D max sum across, and it's the maximum of all the max. Alright, so basically for pre-computation is OHW, because it's your going across every column, and then for every you have to go across all the columns, and for every column is you have to go across everything once to calculate your static sum, and then for your max sum is you have to calculate your x1 and x2, so that's h squared, and then times your width. Right, so here's a sample code for max sum. You can like use it for reference for the questions later. So like now everyone go and try Orchard.
游戏啊，游戏对嘞，这是游戏嘞。
Okay, hi guys. I've noticed that there's no submissions for Orchard yet. Do you need us to help explain the questions? Chakai, are you there? I
What
think we
is your
just, I think we, there's like an explanation for the questions in the slides. I think we just go through them.
Sure. Okay.
Uh,
is anyone still trying?
alright,
Oh,
I will give you some time there.
No, it's fine. Just go through. I'm a bit stuck.
Alright, I'll go through. Let me get the slides. Alright, so basically we replace the zeros with negative ones and then do 2D max sum. Because, so basically what we want to do is like, because since like we are going to be like losing money if we have like a zero inside where the rectangle of one should be. So basically like we can map that as negative one because we're now like in a way like losing money. So yeah, basically making including ones rewarding and including zeros punishing. So basically we do our pre-computation first. So uh, you go to if you go to this page, if you go to this slide where the code is, you see like at the start I for all the height and all the width, we basically we basically like we basically pre-compute our vertical static sums, and then for this next part, so yeah, in this part we have. Wait, Jack, isn't there like supposed to be a second part? Yeah, this. Oh, it's no this is like different from my code, but it's fine. So basically, like remember like in before we had this x1 and x2. Basically, we are basically trying for every possible combination of x1 and x2. In this in this in this code, if we go to the very bottom, in this case it will be I and j. So like I equals 1 and then all the way until h, and then j equals I and then all the way until h. So like it's our start and end. And then basically for all the possible like columns, we we calculate our max sum. which is basically the same as our 1D max sum. So basically the first line column width equals static sum j width minus static sum I minus 1 width is the static is a static sum thing where basically if you go to the slides before, it's the the sum of the blue block is like a minus b. So that's what it's doing in that part of the solution. And then for the next line, you're basically trying to you're basically finding the you're basically doing max sum now, which is basically but instead of like doing max sum on like a normal number, you're doing a max sum of the static sum. Wait, do you guys have any questions?
No.
Right, next part will be, do you guys need any more time to work on this after I explain it, or can we just move on to the next part?
I think can move on.
Right, okay, we'll just move on. So like now there are like we are going to like move on to some other use cases for 2D TP. So like let's say in this case like coin combinations. So okay, wait, can you hear
What's
me?
going on? Yeah.
Right, so basically in some cases instead of like a grid, we have some cases where let's say our DP function has two different variables. So in this case, we also need a two-dimensional we also need to use 2D DP. So coin combinations. So like we have some coins with different values and then find ways to found V cents. But the problem is that so like the same the same type is you can't like count the same thing multiple times. So like it's like 1 2 and 2 1 is the same thing. So this means that our previous DB just cannot our previous DB can't work because our previous DB of like the staircase method just doesn't work. So like our previous method was basically for all the possible like coin values, we just go back. So like if like we're trying to find DB5 and we have let's say we go back to our questions, we have our coins are 1 2 and 4 and want to find the how much how many ways to form 5 cents. We can basically like so like DB5 we can go back 1 step 2 step or 4 steps. So those will be like DB5 equals DB4 plus DB3 plus DB1. So like that's our old solution, but because this solution will count things repeatedly, we can't use it in this case. So we're gonna have to do 2D DP. So let we have let DP IV be the number of ways to get value V with up to coin number I. So like let's say let's say dp, so we have so we have uh yeah, here we have dp ij. I don't know why it's j, but now okay, so j is our like the total value we want to make now. Alright, this is fine. So basically we can have either ways I minus 1 j, which is basically the how many ways we can get this with one less coin, the same value but with like up with, but we put some restrictions on the number of coins we have, or we could have or we could just take or we could take coin number I, which is the second case where I is the same, but j is j you take j minus the basically the value of of coin I, because like so your let's say like if I want to make a value of 5 and I have a coin that's value 2, now it'll be like I'll be trying to find a value of 3 now because I already used up the coin of value 2. So now I'm trying to find coin how many ways I can make like a value of 3. So that's how the logic works. It's like we go to the table and we update this row by row. So let's say our I is 1 and the value, and we're trying to like find out all the possible values we can make. Now because there's only one coin, so there's the first row is all ones because there's only one way of making that. Now if you go on to the next row, and then let's say you want to make a value of 2 with the coins of up to value 2. Wait, Jia Kai, can you move the slides? Move it up to here, like with the two choices. Yeah. Right. So basically, you can see we are basically grabbing the values from the one above it or the one that's like two steps to the left. So basically the one above it is that we're just ignoring we're just ignoring our new coins, and we're still like using the old method, and we're still basically using all the possible ways of doing it with the old method, which is like up to 1. And then or we could do or you could basically take the value or you could basically take one of the new coins, which will basically put us back to this column with value 0, which will basically like put us 2 columns to the left because that's the value that's the difference in value of the coins. So it's the same thing for the third row. And as you see, we've now filled out our DP table and it's correct. Now go try the coin combinations problem on Codebreaker.
Oh no. Wait.
No, it's definitely so that you can hear the stream and not like both.
Do you guys need more time with coin combinations, or do we just move on? Because we are a bit short on time. Like it's like we have to at least finish like knapsack, because like that's a very classic problem you have. And then like knapsack and then list. I think the other one, the other two will just skip. So you want to do knapsack.
Alright, okay, so snap. Ah, my brain cannot work.
It's kind of important.
Okay, so snap neck. Okay, so this is the code for coin combi. Just like look through it. Alright, snap neck. So this is 01 knapsack. So we say we have a bag that can carry up to weight W. Then we can choose up to n items, which has weight Wi and value Vi, and then we want to find the maximum value we can carry in the bag. So yeah, so let's say this is our Wi and our Vi. So we can let's say the max weight is 10, and so we can take the coin with 5 and 10. Then we can take 2, and then we can take 200 to get $112. Then we can get 10 2 for $2 or 611 for $11. Can we take greedily take items with highest Wi over Vi? You might be thinking that is possible greedy, but no, I don't know whether there's a proof here. Okay, no. Okay. So the thing is, I think one counter example is let's say you have a bag of max weight 200. Okay, you know what? I'll just edit the slide here. If the we'll just okay, fine. For just for the sake of this, let's say we have 200. We have a max weight of 200, and then we have a current value of 0. Then we clear this table. Then let's say it's a row below. We have 100, 1000, then 100. Wait. Let me think. Hold on. Let's say 10,000 for the sake of it. 10,000. Then here we have 99, and then 10. Sorry. Oh yeah, 199 with 19,999. So clearly the greatest Vi over the greatest value for weight is this thing, because this is 100. But by taking this, you're limiting yourself to 19,999 instead of 200. Instead of 19,999 instead of 20k. Yeah, that's a simple counter. That's a simple counter example lah. Blah blah blah. Can you try all 2 to the power of n subsets? Yes. But you will need a bit of time to compute. Just a little bit. You might die in the process, but just a little bit. Okay, so let's think about possible states. What about one DDP? So dp of I goes to maximum value given weight of I. But how about the items? So we might need so that's why we need 2 DDP. So what transition? So we can either take item I or don't take item I. Wow. So let dp of IW be equal to the maximum value after considering taking I items and having a maximum weight of W. So we can build up from a previous state. We build up to dp IW from something less than I, something less than W. So, I think this is pretty intuitive. So DPIW, what are yours? So you have to think what can you come to this from? So you could either actually I'm pretty sure this doesn't matter. I'm pretty sure this will do the same thing. DPI minus 1W is to not take W item I, or you can take DPI minus 1 W minus weight I plus basically take item I. Note that when you take item I, you add value I into your return value, and then after that your maximum weight you can take decreases by weight I. So yeah, so basically this is quite intuitive lah. So here we go. So for example, if maximum weight is 0, then you can take the coin of value 2 here, then coin of value 2, coin of value 2, coin of value 2. Now if you consider this item, we can consider, so it's just max of this and this, so it's still 2, because you can take this, then after that you continue on. You can take this, you can either take coin 5, or you can either get rid of coin 1 and go for coin 2, or stay loyal to coin 1, so it's 5, then 7, because now you can store both coins 1 and 2, and then you just continue. Then same thing here, you realize that it's not optimal to get rid of stuff, so yeah, then you realize that you can from here onwards you can take every single coin now. Yeah, basically. So our answer will be DP of NW. So do coin back or 0-1 knapsack. Snap neck. Snap neck is another problem actually. Hopefully my mic is on. I try doing coin back or 0-1 knapsack. I think we'll give you until like 3:40 to attempt. Then after that we'll just go on. Because we already told you the state. After this it's just, hold on. LCS. I think that's all. Wait, it's mainly just 2 DTP. Let me just check. Yeah, it's just LCS, Levenstein, and then LIS. It's just that. Oh, that's a lot of content to cover. But yeah. 37. Do you want to continue or do you need 3 more minutes? It's an either or question. It's not a thumbs up emoji question. That's the opposite of continue. Yeah, that's the opposite of continue. Okay, fine, I'll continue. Alright, let's go. Okay, from our very original slides, as you can see here, this is not a screenshot. We actually designed this slide. Yeah. So this is the code basically. Yes. You can do it on the fly too. Yes. Okay, LCS, longest common subsequence. Given 2 strings, what is the length of the longest common subsequence between them? For example, between banana cat and inane chatter, the LCS is nan cat, which has a length of 6 letters. So we look at the prefixes of A and B, and then if they end with the same letter, then it is basically 1 plus. You minus the suffix of LCS of ba and e. Similarly, it is if they end with different letters, then you can try you remove 1 letter from each string. You remove a letter from each string, and then after that you evaluate separately. So in code terms, LCSIJ is let LCSIJ be the LCS between first I letters of A and first J letters of B. So if AI is equal to BJ, then we can just -1 plus 1, or else it's just the max of I minus 1j and ij minus 1. So yes. So if you look at this LCS function, so it is basically if you look at this, t equals to t, so you just take it from so it's just this plus 1. Then for this, a equals to a, so it's just this plus 1. Then for this, h is not equal to c, so you take max of this and this, and then you just evaluate so you just evaluate this lah. C equals to c, so 3 plus 1 4 3 3, yeah. So basically this is basically your function. So solve it. Wow. Yeah, it's not that hard. You get pseudocode, I guess. It's actually, yeah, it's just this. Actually you should I'll just add it to a problem set. I think we'll just rush through LCS because LCS is quite easy. Bottom up, top down, same thing. Okay, so let's go through Levenstein. Guess problem reference. So given 2 strings A and B of length n and m, change A into B in as few operations as possible. Insertion of a character, deletion of a character, or substitution of a character. So to solve this problem, we define a function edit ij to be the distance between the first I letters of A and the first J letters of B. It's kind of like the LCS. It's just, yeah. Then obviously if AI is equal to BJ, we don't need to substitute. So So edit ij equals to edit I minus 1 j minus 1 plus 1. If ai not equal to bj, if not, you just edit I minus 1 j is equal. But then for this is for substitution. If you use an insertion, we will add bj after ai or insert ai after bj. So edit ij equals to min insert to b and insert to a lah. So basically you edit 1 minus 1 j by adding a new letter, or edit 1 j minus 1, basic I j minus 1. So you add a letter to the second string b. So if you use a deletion, same thing, we minimum of delete from a, delete from b. So it's the exact same as insertion. So put all these cases together, you get this is almost LCS. So obviously if you have 0 characters as your string b and I characters in string a, the most efficient way is to just add I characters from string a to string b. So edit I0 equals to I. In a similar fashion, edit 0j equals to j. And for edit ij, you have this, which we just explained. So it's the minimum of all this because we want the minimum level. It's a minimum amount of substitution, additions, and deletions. So yes, this is the code. Yeah. What else do we have? Just check. There is list and log. Okay. Oh my days, what do I press? Okay. I think what we're gonna do is we're going to speed run through this. So we're going to just read through this at our own time, try to digest it. But because you only have like 16 minutes left, I think it's wiser for me to just continue. So list in n log n. So list easy is on squared. We have gone through that before. If you haven't done that, try to do that. Yeah. How to do in n log n? It's clearly not 2D DP. Yeah, because if you have 2D DP, you have probably n squared states, so you can't really get that log n factor. So, using the previous n squared algo we learned, so here for list, you ask yourself, where can I come from? So you come from 2, for example, from here, I think. So n log n, for n log n, what you do is that you realize that we don't need to use an array to store the list that ends at each index. We can just use a single vector. So for every element to the left, we can check or not. Oh, this is asking. Yeah. So for every element to the left, we can check whether it's larger than the current last element of the list. If yes, we can just push it to the end of the vector. So 1, 2, 5, 6 is clearly fine. Then so this is the actual. So your vector contains your actual list. So we can just do 1, 2, 5, 6. Then what about 3? So if 3 is less than 6, where is the most suitable place to put a 3? Obviously, you realize that it is always better to put it after the maximum element you can put it behind. So it's the maximum element less than or equal to 3. So what happened?
Does anyone need help with coin back?
Wait, less than 3, I think. The maximum element less than 3, which is 2 in this case. Okay, then so it is greater by not replacing the 2, you are giving it a better chance, a better potential to for the list to be longer. so you can make it 3. But so for 4, you can roll out now that it's 1, 2, 3, 6. You can make it you can replace this with 4 and then 5. You just push it back to the list vector. So without replacing the 5 and 6 with 3 and 4 respectively, we will not have been able to push the 5 at the end. So yeah, wow, trade-offs. Okay, let's go. So for every AI, we find the smallest value using lower bound. We will find the smallest value in the list vector, which is greater or equal to AI, and then we replace that value with AI. So that's n log n. Is that all? Yeah. Sample. This sample code. So you look. This is our array. Our list array. Then after that we syn array I. Then if v.mt of if this is our first element, this is the first element of the list, or that if we can append it to the back, we can just simply append it to the back, or else we set it to lower bound. We set lower bound v.begin v.end array I to be equal to array I. Note that because for every pushback operation, it is guaranteed that it is possible that the list is strictly increasing. Hence, you can just simply return v.size. So you don't need to worry about 1, 2, 3, 6 not being a possible list, because at the time of 6's insertion, it was 1, 2, 5, 6. So if you're wondering about that, yeah, it's considered 4 because at the point of insertion, you are guaranteeing that this is a valid increasing sequence. So you have already so v.size is the correct answer. Yes. These are the some extra problems for you to do. Yes. Is there any more to Orchard 2 too? Yay, slides entered. It's 3:50. Okay. I think
Meow.
you do realize that this is being recorded and it will be uploaded to YouTube. Okay. Anyways, is there any more questions that you all may have about DP2? If not, I don't think we have anything else. Oh no, I don't have water. Yeah, I'm going to die of thirst. Okay.
I'm currently typing up a Wikipedia article, not really, but yeah, not so quick note about states and transitions and
Okay.
why list is O n log n and list easy is O n squared. Right, just wait.
Wikipedia.
Why are you looking at Wikipedia?
I'm not. I'm typing my own like quick note, but it's like
It's not
very
quick. You've been typing for the past 10 minutes or something, bro. Okay. Meanwhile, I'll try these problems. I will try to get them up on Codebreaker soon.
What are you typing?
He's typing a Wikipedia article. It takes a long time to type Wikipedia articles. It would be very funny if you hit the character limit. Oh. Oh. I see. It's not really a Wikipedia article. Alright, any more questions? About list, anything. List, LCS, Snapset, Levenstein. It's actually very quick to read. Okay. Yes, I think if there's nothing else, I think we can just dismiss them. Right, Jinxuan? I think it's okay.
Yeah, I think we can just dismiss them.
Okay, bye bye.